chapter number 7, and we are about to finish our course. So actually, we have several cases for modeling, as I told you in the introduction. We start from a very simple model case, and we can motivate this why we are considering this simple case or single phase flow. And we could have two-phase flow or three-phase flows or black oil model and so on. So we'll start one by one or step by step, explaining each of this model and how to solve it and all the possible scenarios we can discuss. So for the primary production, as you know, it is just once we drill and open the production well, oil comes out. Why? Because the huge difference between pressure inside the reservoir and outside the atmospheric one. All right. As you can see here, this is just a schematic diagram showing reservoir. It is not real one, but schematic one. Usually we have water reservoir or aquifer water or brine will be in the bottom of the reservoir. Then we have we have a thickness of oil only, and then gas at the top. Then we have cap rock and the crust and so on. This is just schematic diagram. So here we have high or very high pressure in the reservoir. So in the beginning, engineers or petroleum engineers start with drilling production well only. So production well. So once they have it and open it for production, oil comes with the drive or the help of pressure drive. Actually, pressure drives flow here, so the flow will go up very quickly. So why the model here is single phase? Because actually the model here, the well is injected until reach the oil region. All right. So we'll have only oil. So it is single phase. So it doesn't mix right now with gas or if you remember the Darcy's law or momentum conservation equation, we wrote it like this. We have a velocity. Velocity is a vector. Vector means it has a component. Each of it in one Cartesian direction, it will be ux, uy, uz. I will explain later. And key is the permeability. And this nabla is called gradient. First derivative also in different direction. Could be dB by dx or partial b by partial x, partial b by partial y, partial b by partial z. So this is in general case, could be 1D, 2D, 3D. And as we simplify or we define our problem, we can go and try to solve this one. By solving this equation, we must know what? Velocity and pressure. But we have a problem here, a mathematical problem or mathematical issue. We have single equation in two variables. So we'll not be able to solve this equation unless we have another one to be coupled with this one and in U and B in these two unknowns. We don't have information about velocity or pressure. They are related. Yani, Darcy's law is telling us that U is or velocity is related to pressure, but we'll not be able to know them unless we have another equation. The second equation will be the continuity equation. The continuity equation, which is the divergence. Divergence of velocity equals the source or sink here. So I will later maybe focus on what is the difference between source and sink. So I will also derive the continuity equation, but now just consider continuity equation like this. So now we have two equations. The first one, which is Darcy's law in U and B, and the second one in U, which is the continuity equation. So combining these two equations together, will be able to solve them or to find a unique solution. All right. So we'll just bring the right-hand side from Darcy's law here and substitute here, which I colored in green here. It is not necessary to have B here, pressure. All right. Q is constant, a given constant.
Okay.
So we'll just substitute it here, and here, the last equation in this slide, we have what? It's equation of second derivative. We have derivative here, right, which is a gradient, divergence, and another one here, and B. So this equation is a single equation in one variable, right?
Yes.
So we can solve it to find pressure, Once you calculate pressure from this equation, then we'll get back to Darcy's law. Now we assume that we knew pressure by solving the last equation, right?
Yes.
So we'll substitute back in equation number one, or the first equation, Darcy's law, we'll get velocity. Now let's expand or rewrite our Darcy's law in 3 dimensions. This one is Darcy's law. Now you can expand them in each direction. So in X direction, Ux, and we used here, and you can know now, or you can notice the difference between this this one is bold, represent vector, but Ux here represent what? Represent component, okay? So, and here, the small k here is just the value of permeability, and mu is the viscosity. So just I wrote the velocity vector like this. So the velocity vector had 3 components, but the pressure P is not vector. It's not a vector. It's a scalar quantity.
Yeah.
And pressure has no
one value,
yes. Just one quantity, a scalar quantity. That's why the gradient also is partial B by partial X. You know, partial means D as a derivative, but in partial sense because U and B now are functions of X, Y, and Z. All right. So all derivative would be partial derivative, not exact derivative. So we have, for Darcy's law in 3D, we have 3 equations. All right, Ux, Uy, Uz. Clear?
Yes.
Okay. So this case again is a incompressible single phase flow in porous media. Yeah. Also, you may remember the divergence. When we have dot here, it's unlike gradient nabla B, all right? This one is pressure gradient because B is scalar quantity. So this one gives partial B by partial X, partial B by partial Y, partial B by partial Z, could be plus. But this one, if you remember, because nabla, or the operator nabla, is defined as this one, is a vector also, right? And velocity, another vector. When we have dot product, we call this one the dot scalar product or dot product, right? So the dot product is just give 3 scalar variable like partial Ux, by partial x, partial y, partial y, partial z. Then when we substitute this one in the continuity equation, which is this one, huh? This one, right?
Yes.
When we expand it, it will be written like this, okay? In 3D. If we are talking about, if we simplify our model, then we will drop this one. If we simplify our model to 2D, then we will drop one component. If we are simplifying our problem into 1D problem, we'll see some example, we'll drop this one, and this one will have only one component, all right? So also, this equation, the last one, I mean the pressure, by the way, we call this equation, can you see where I am pointing?
Yes. Yes. Yes.
So we call this one pressure equation, because now we can solve this one to get pressure only, and we rid of velocity, maybe temporary. So this equation can be written in this form, of course, yeah? And it can be expanded in x, y, z like this, all right? So from where we got this is second derivative, correct? Yeah? Second derivative. And this one is also second derivative, but in vector form. This one in expanded form, or in x, y, z means. This means we have the divergence here, and instead of having ux, uy, uz, we'll replace them by partial b by partial x, partial, and having it in this form. But you have what? You have k over mu here. We'll take this constant. By the way, they are constant now. K is constant, the permeability is constant, just numbers, and mu also for this incompressible simple case flow, it's incompressible because it is liquid. So we'll take this one to the right hand side to be mu over q, right? With a negative sign. We move also the negative sign to have this one. This one also, it's a simple one, but for analytical solution, it will be in special case, or some special cases, we can get a solution for this one. For 1D, it is easy. We can see, we can just directly integrate. For 2D also, it's available for some special cases. But for 3D, we prefer numerical solution. We prefer numerical solution to have it. By solving this one, it will give you a map or distribution of the pressure in all the domain, in all the reservoir. Then I'll get back to the Darcy's equation, substitute in the pressure, you will get also information about velocity, and you could have the information needed about this problem, or flow description in the reservoir.